Welcome to CS Course Companion. You write a line of code and you expect the computer to just get it. But what if I told you that sometimes it gets just as confused as we do?
I mean, look at this. X minus 2 times y. For us, the answer is a no-brainer, right? But for a computer, well, this simple little expression is a real puzzle. See, without a clear set of instructions, a computer might see this one expression in two totally different ways. That means two very different answers, which, could be catastrophic. One problem, two completely different meanings. So, how is that even possible? Well, in this explainer, we're going to pull back the curtain on how computers actually read code. We'll dig into why this simple math problem can cause so much confusion, and then we'll look at the clever rules we create to make absolutely sure our code is understood correctly every single time.
Okay, so it all starts with this really critical piece of software in every compiler. It's called a parser.
So the parser's job is pretty simple, but it's super important. It reads your code, checks if you followed the language's rules, and then it figures out the underlying structure of what you're actually trying to tell it to do.
It's a lot like when you had to diagram sentences back in English class. Remember that? Finding the subject, the verb, the object. A parser does the exact same thing, but for code. It has to find the structure to understand the meaning.
And here's the key. The parser doesn't just guess. It follows a super strict rulebook, a formal set of instructions that we call a grammar.
Grammars can actually be incredibly simple. Take this one for sheep noises. All it says is that a sheep noise can be another sheep noise followed by ba, or it can just be ba. Yeah, it's a bit silly, I know, but it perfectly shows how a set of simple rules can generate all the valid sentences in a language, from ba to ba ba ba, and on forever.
All right, so now that we've got a handle on what a grammar is, let's see what happens when we apply a simple but, flawed grammar to our original math problem.
So, by following the rules of our grammar and always replacing the leftmost variable, the parser can build out our expression, step by step. But the real magic here isn't just generating the text, it's all about the structure this process creates. And what this process does is it builds what we call a parse tree. You can see this one groups the multiplication first, which gives us x minus the result of 2 times y. Okay, so far so good, right? That's the answer we all expect. But here's the catch. What if the parser makes different choices? What if it follows the exact same rules, but this time it always replaces the rightmost variable instead? Well, believe it or not, it can still generate the exact same string of code, x minus 2 times y.
But whoa, look at this. The parse tree is completely different. This new structure groups the subtraction first, which leads to a totally different and, completely wrong answer. And this right here is the heart of the problem.
And that brings us to the crucial point. Our grammar is ambiguous. It's created a situation where a single piece of code can have two possible meanings. And for a programming language, where predictability is literally everything, this is an absolute disaster.
Okay, so how do we solve this mystery? How do we write a better rulebook that forces the computer to find the one and only one true answer?
So the culprit is this one rule right here, Expr, Opscher, Opscher. It's just way too general. It treats addition, subtraction, multiplication, all of them as equals. It completely fails to teach the computer that order of operations thing we all learned back in grade school.
So the fix is to rewrite the grammar to actually build in the concept of precedence. We do this by creating different levels, kind of like term and factor. Think of it like this. By making multiplication part of a term, we're telling the parser, hey, you must deal with this multiplication stuff first, before you can even think about the subtraction, which lives up in the bigger expert level. So now, when the parser tries to understand our expression using these new, smarter rules, it's forced down a single correct path. There is literally no other choice it can make.
And voila! No matter which derivation we use, leftmost, rightmost, it doesn't matter. We get the exact same parse tree every single time. And it's the right one, the one that respects the order of operations. The ambiguity? It's gone.
And this isn't just about getting your math homework right. Ambiguity is this sneaky problem that pops up in other really critical parts of programming, like the classic dangling else problem.
Just take a look at this nested if statement. See that single else at the end? Okay, so which if does it belong to? An ambiguous grammar allows for two different interpretations. And this might seem like a small detail, but depending on which if gets that else, your program could do something completely different.
I'm not kidding, this exact problem has led to real-world security bugs that are an absolute nightmare to track down.
Okay, so after all that, why does any of this matter so much? Let's do a quick recap of the big takeaway here.
You see, designing these precise, unambiguous grammars, it's like the invisible foundation that makes all of our software actually work. It's what ensures the commands we write are predictable and reliable. It's how we guarantee 100% that our code does exactly what we tell it to do every single time.
It really makes you wonder, doesn't it? What other fundamental, invisible rules are working tirelessly behind the scenes of the technology that basically powers our entire world?
So if this explainer helps you finally wrap your head around parsing and ambiguity, I'd really appreciate it if you'd hit that subscribe button and join our community here at CS Course Companion. And seriously, I want to hear from you. Let me know in the comments what other computer science topics you're curious about and want to see broken down next. Thanks so much for watching.